Let us use an analogy to understand electric flux better. Consider water flowing through a rectangular open channel at uniform velocity and draining into a measuring jar. A valve, V1, is introduced to regulate the quantity of water flowing into the channel. The discharge, which is the quantity of water flowing per unit time, is given by the product of the velocity and area of cross-section of the opening of the regulating valve. To regulate the discharge, we increase the open area of the regulating valve, V1, assuming that the velocity of flow of water upstream remains constant. Let us install one more valve, V2, downstream to V1. V2 is pivoted to the bottom of the channel. Valve V2 can swing about a horizontal axis, which is perpendicular to the direction of flow of water. This completes the apparatus. Now for the experiment. Keep the area of the opening in both the valves the same. That is, the bottom line of the closing plate in the two valves should be at the same height. Measure discharge Q1 for 5 minutes by collecting the water in the measuring jar. Keep this measuring jar away from the downstream flow. Now, lower the closing plate of V1 without changing the position of the plate in V2. Measure discharge Q2 again for 5 minutes. Q2 will be less than Q1 as the area of opening in V1 has decreased due to the lowering of the plate. Then, swing V2 until the bottom line of the plate just touches the top surface of the water in the downstream. Remove valve V1. Measure discharge Q3 again for 5 minutes. You will find that Q3 is equal to Q2. Why is Q3 equal to Q2 when the area of opening of the two valves is different? This is because the area of opening of V2 is more than that of V1. V1 is kept perpendicular to the direction of flow of water, whereas V2 is kept at an angle to the direction of flow of water. The projected area of opening of V2 taken on a plane, which is perpendicular to the direction of flow of water, is equal to the area of opening of V1 that is kept perpendicular to the direction of flow of water. What are the conclusions that we can draw from this experiment? Q is equal to V into A, where V is the velocity of water flow and A is the area through which water flows. In this equation, A should be perpendicular to the direction of flow of water. In the event A is not perpendicular to the direction of flow of water, we should take the projected area on a plane perpendicular to the direction of flow of water. Then, the equation will be modified to Q is equal to V into A cos theta, where theta is the angle that the outward normal to the plane makes with the direction of flow of water. Here, V and A are vectors, and as Q represents the quantity of water, it is a scalar. Mathematically, we can write the equation as Q is equal to the dot product of V and A. Electric flux, phi, is analogous to Q of water. Like Q, phi is also a scalar quantity. However, unlike in Q, where there is flow of water nothing flows in electric flux. There are only imaginary electric lines of force that cut across the area. Uniform electric field E is analogous to the velocity of water V. Mathematically, we can write the equation as phi is equal to the dot product of E and A. We can now extend this equation to curved surfaces with electric field of different magnitudes and directions at different parts of a given surface. The SI unit for electric flux is Newton meter square per coulomb. This brings you to the end of this introductory module on electric flux. You will learn more about applications of electric flux in coming modules. Consider a uniform electric field of strength E along the x-axis. Consider a rectangular surface of area A placed in the uniform electric field such that its axis makes an angle theta with the direction of the field. In other words, the area vector A, which is conventionally taken along the outward normal to the surface, makes an angle theta with the direction of the electric field. The electric flux passing normal to this area is then given as phi is equal to E dot A or phi is equal to EA cos theta. Now, consider a closed surface S placed in the uniform electric field of strength E. Consider three elements X, Y, and Z on the closed surface, having areas delta A1, delta A2, and delta A3 respectively. The electric flux through the element X is phi 1 equal to E dot dA1, and since the angle between the direction of the electric field strength E and dA1 is acute, the flux phi 1 through this surface is positive. For all such elements, the flux passes from the outside to inside. That is, they have an inwardly normal flux. Since theta is equal to 90 degrees for element Y, the electric flux for Y is equal to 0. For all such elements, the flux through the surface is 0. Similarly, since theta is obtuse for element Z, the flux through the element is negative. For all such elements, the flux through the surface passes from the inside to outside. That is, they have an outwardly normal flux. From these observations, we can say that the inwardly normal flux is negative and the outwardly normal flux is positive. Let us now consider a point charge plus Q placed at the center of a sphere of radius r. Let us now look at Gauss' law, which defines the relation between the net electric flux through a closed surface and the charge enclosed by that closed surface. This law is of fundamental importance in the calculation of electric field strengths. The closed surface is referred to as the Gaussian surface. The electric field lines of the point charge plus Q are outwardly normal to the charge and hence are outwardly normal to the sphere at all points on its surface. The magnitude of the electric field E at a distance r from the point charge is equal to 1 by 4 pi epsilon naught Q by r square. Let this be equation 1. So we see that for all points on the sphere of radius r, the magnitude of the electric field strength is the same, and it is directed away from the charge plus Q in an outwardly normal direction at each point. Therefore, we see that at each surface point, the electric field strength E is parallel to the area vector dA, which represents the area of an infinitesimally small element on the surface. Since E is parallel to vector dA, the electric flux d phi passing through this local element is equal to E dot dA is equal to E dA cos 0, and as cos 0 is equal to 1, d phi is equal to E dA. Let this be equation 2. To find the total electric flux phi through the Gaussian surface, we now integrate d phi. Therefore, phi is equal to integral d phi, and this is equal to integral E dA. The total electric flux can also be referred to as the net electric flux. Since E is constant in magnitude for all points on the Gaussian surface, we have integral E dA is equal to E into integral dA. We know that integral dA is equal to A, which is the area of the Gaussian surface considered. Now, phi is equal to EA. We know that for a spherical surface, which is the Gaussian surface in the present discussion, A is equal to 4 pi r square. Therefore, we have phi is equal to E into 4 pi r square. Let this be equation 3. Substituting equation 1 in equation 3 and simplifying, we get the net flux phi is equal to Q by epsilon naught. Let this be equation 4. We see that the net flux phi is proportional to the charge Q enclosed by the Gaussian surface, or we can say that the net flux is proportional to the charge inside the Gaussian surface. Now consider two other closed surfaces, S2 and S3, around S1. We see that since S2 and S3 are closed surfaces, they can also be referred to as Gaussian surfaces. But it is important to note